So, about last week, maybe a couple days ago, I bought this Atari emulator, little thing where you could play old Atari games on it. I stumbled upon this game called Cannonball that's on the screen right now. And you have to shoot humans into the basket, but I missed. I kept missing. So it got me thinking, is there any way I could apply physics to this and actually figure out how to land it in every single time? So I put my brain to this, tried to figure it out. I had to unload the book of physics on this bad boy. Because, you got to figure out those equations, what to use. But this is just all a huge projectile problem. So what I did here is I got 3 data points at 80 degrees. And you can see with the tape there, that's to mark when the displacement is 0. And here I'm speeding it up on some of the work I did. I was changing the miles per hour into meters per second because I like working with that metric system a little bit better. No offense to the US system. I don't want to offend anybody. Maybe not. But I'm doing this here. And the first one I do is the 32 mile per hour projectile, which is about 14 meters a second. And to do this, I find the y component of this velocity and the x component. And what I unload, or the equation I use, is vertical displacement equals the initial velocity of the y multiplied by time plus 1/2 acceleration times time squared. And the displacement would be 0, which I did with the tape. And I plugged in the velocity and the time. I did 3 tests and found the mean of the time of when the projectile, the human, hit that tape again. And I timed this, and I found that acceleration in this isn't 9.8. It was actually 8.6. I tested it with all 3 projectiles to make sure I wasn't wrong. As you can see here, I'm testing with the 35 mile per hour projectile, and it came out to 8.58, which is close to 8.6, and the second one came up a little bit above 8.6, so I made 8.6 the acceleration. And is it on Mars? Because Mars is the closest planet with this acceleration. So I thought that was interesting. And here I used Logger Pro because I didn't want to use my ruler and measure the screen. So I knew how far he went by taking the x velocity and multiplying it by the time that he was in the air, and that's the displacement in the x direction. So I did that from the cannon to where he was, and then I found interesting things of each, and I found how far the basket is, how long of a distance it is. And doing this, I knew that the change in x had to equal 16.78 through 20.63 meters. So I knew somewhere in that target, when I plugged in numbers, that's where my target had to hit, with a vertical displacement being about 0 because the angle changes, so it's roughly 0. And at 43 miles per hour I was doing this, and I used an angle of 78 degrees, which worked. I plugged it into the equation, vi times t plus 1/2 acceleration t squared, and I turned it into a quadratic equation. And then using that, I could use the quadratic to calculate the time, which I did so. And then multiplying that time by the initial velocity and the x that was found here, I find that distance that is found is less than the 20.63 meters. Barely. But it's still less, so that means that this projectile would make it into the basket. And then this here is just me repeating the process at 35 miles per hour, which also works. I used a angle of 68 degrees. Yeah, that's the angle I used. And that angle worked too. And then I kind of just sped it up here of me finding, or skipped actually, the time that it was in the air multiplied by this velocity in the x. And I get a number higher than 16.73 and less than 20.63. I believe those are the numbers. But this one also works, meaning that it makes it. So this is a go. This is what works. A good angle. So the 35 and the 43 mph projectiles checked out. I also did it on the 32 mph one, but I didn't want to put it into the video because that kind of made it too long and was unnecessary. So after all this, I opened Cannonball again with my newfound knowledge. I tried to go 7 for 7, taking all this into account, calculating the angles. I played around with it before I recorded this video, of course, you know. I don't want to act like I'm too good, like I was, you know, Kobeing all these shots. But I'm just making them fall, because with physics, you can just predict anything. You know what's going to happen. That is the point of science, to be able to accurately predict what will happen in the future. Well, not necessarily. It's also the discovery. But I went 7 for 7 here using physics to find all this out. And after I did this, I found a weird little thing that for speeds between 28 and 32 miles per hour, all you would have to do is add 29 to those numbers, and that would be the appropriate angle to use on your projectile to make it into the bucket. And then for speeds from 33 to 38 miles per hour, 40, and then 42 to 45 miles per hour, if you add 33 to the mph number value, that would be the appropriate angle there to score into the basket. And then the oddballs out were the 39 and 41 miles per hour, where you would have to add 34 to that number value for this to work, which was a little odd for it to be like that. But to explain this, you could just do the, I'm just going to call them the triangles, like I did at the beginning, to show the value of the velocities in the y and the x. And if you did that, found the time that they were in the air, that would explain why this occurred. Thank you for watching my video. Hope you learned something. Thank you.